Hi there, I'm Clint O'Block, and today I'm going to be talking about securing APIs in financial services, and we're going to be using a zero trust mesh network to do so. Let's go ahead and take a look at what that means. Usually, when I tell people I work on a zero trust mesh overlay, this is the reaction that I predict I'm getting internally, sometimes externally, but usually internally. People are like, zero trust, what's that all about? It's such a marketing buzzword nowadays. It's kind of been uh, turned into something where this is most people's normal reaction. And hopefully by the end of this talk, I'm going to convince you that it doesn't have to be like this. So as usual, you have a slide that talks about yourself, but since this is a virtual presentation, you can't see me. You don't know that that is definitely not me. That's my friend Philip, who also works with me on the OpenZiti project. And Philip said something to me one day that has stuck with me. And he said, developers don't care about security. And I can understand where he's coming from. You go to Google and you type that in, and you're going to get all kinds of stuff. Why don't developers do security? Do developers care about security? Why do they dislike security? Blah, blah, blah. Realistically, at the end of the day, I think it's not that developers don't like security, don't want to have a secure application, don't care about security. It's that we're too busy doing other feature work. There are lots of demands on developers, and all too often security is just one of those things that people push away and push off to the end. But 10 or 15 years ago, I found this great quote from Joel Spolsky, and he created Stack Overflow as well as some other things. But he has this great quote that I love to this day, and that quote is, shipping is a feature. Your product must contain this feature. And that's such a great quote. It's basically telling you, hey, you've got to ship. Don't sit there and try to make everything perfect. You have to ship. And it's one of those things that people don't notice, that shipping is actually something to be considered a feature, just like security is a feature. Your application must be secure. Your application must have this feature. Security needs to be something that we stop pushing off to the end, stop treating as an afterthought, and actually give the time to. And that means if you're a product owner or a product manager or a VP of engineering, give your developers time to actually secure their services properly. So, who but me? This is actually me. I've been a developer for a long time. I spent a long time in Java and C Sharp and now Golang and C. Spent a long time doing IoT work, but my entire career has been about APIs and securing APIs. So let's look at what current technology is when it comes to network security. Generally speaking, when you think of network security, you think of the castle and the moat. And when you're in the castle, when you've gone over the drawbridge and gotten through the walls, you are safe and secure and you are considered trusted. And this was how it was for the longest of times until people started getting breached and we started realizing, hey, maybe insecure traffic on our network is not the way to go. These are services using HTTP because you could, or FTP because you could. It's the private network. It's safe and secure. Well, we decided that was a bad idea. And so like 15 years ago, people said, "Hey, let's stop doing that. Let's put TLS everywhere, transport layer security. Let's make sure even if there are bad guys, we're going to make it really hard on them to actually do anything with the particular traffic themselves. We're going to have transport layer security." And everybody's like, "Hey, that's great, fantastic," but it doesn't stop all of the problems, obviously. This was actually such a good idea that a couple of projects spun out of the idea of TLS Everywhere. One was HTTPS Everywhere, a browser plugin that would upgrade your browser silently from HTTP to HTTPS, just sitting there ever vigilant on behalf of the users. Such a good idea that every browser now does this, and the Electronic Frontier Foundation, who provides HTTPS Everywhere, has said we're going to stop providing it because the browsers just do this now as they should. And then Let's Encrypt. Let's Encrypt was a project started out of the need for easy security, easier or cheaper. In this case, back in these days, you had to have a self-signed certificate or you had to pay somebody to get a legitimate certificate. You couldn't have the nice lock icon without a legitimate certificate. Let's Encrypt made that free and easy for everybody. So that was fantastic. A couple other projects that are now doing this same sort of thing are SPIRE and SPIFFE and OpenZiti, the project I work on. Um, SPIRE is all about short-term certificates and bootstrapping trust in a way that is easy and implicit, whereas OpenZiti is a zero trust overlay network and takes zero trust in a slightly different direction. SPIRE also has some zero trust aspects to it, which we'll see. And SPIRE is also a CNCF project, Cloud Native Computing Foundation. They've also graduated, which is a pretty big deal. Not very many graduated projects from CNCF. Here's our agenda. We're going to do a real quick overview of Zero Trust, a real quick overview of SPIFFE and SPIRE and OpenZiti. We'll combine OpenZiti and SPIRE, and then we'll see how we can secure our APIs all in action. And we'll take a look at all those things. So let's get through a few foundational tenets of Zero Trust. These are the ones I find to be probably the most important, one of which is device identity. So device identity means every single device has a strong cryptographically verifiable identity associated to that device. And that's great because then once you have that strong verifiable identity, you can make certain decisions with traffic. But you can also take this one step farther and not have a device identity, but instead have a workload identity. Workload is a fancy term for some process that's running on some computer somewhere. So if you have multiple identities on your local computer, well, that's even better than one identity on your local computer because now you can authorize individual services or individual service clients, etc. The next pillar of Zero Trust is least privilege. Least privilege comes along with that strong identity because now the network can start making decisions like, hey, this user who has been compromised, they are not authorized to send packets to the device which they're trying to send packets to. So Zero Trust is about reducing the level of privilege out of the gate that a device has or a workload has. So least privilege, really important, strong pillar of Zero Trust, of any Zero Trust network. And then continuous authorizations or posture checking. So this just verifies constantly that the device is still able to connect to a network or still able to connect to a service to do the things that it's supposed to do. And it does this continuously so that if a workload or a laptop gets compromised and the attacker starts sending packets, well, the network knows the attacker doesn't have, say, a time-based one-time passcode, a TOTP, and won't even allow you onto the overlay network without having the correct posture. I like this slide because it represents how the journey is from an insecure API to a secure API. This is the longest path a person can walk across the globe. And like this path, it is a journey to secure your APIs. So we're going to start with an insecure server, and we're going to take that through mutual TLS and all the way into a Zero Trust overlay network. And we'll see that happen here in a little bit. Don't be surprised or don't be sad if you stop somewhere along the way. It takes a long time to get to a fully secure service. Hopefully I can convince you it's not quite as long as you might think, particularly with SPIRE and OpenZiti. So let's talk about SPIRE. What is SPIRE? It is the SPIFFE runtime environment. So you'll hear SPIFFE and you'll hear SPIRE used all the time, oftentimes together. SPIFFE SPIRE is what you'll hear a lot. And if you go to their website and look at the tagline, they're claiming to be the universal identity control plane for distributed systems. So they have some use cases on their website too, which they think are key use cases. Securing microservices, obviously what we're here to talk about. How are we going to make our microservices, our APIs, more secure, either intra communication or client to server based communication. Authenticating the databases, building bridges, the same normal stuff. I have a lot of slides and a lot of material to cover, so I'm going to go really fast. I hope everybody can keep up, and if not, please ask questions after. Well, I mean, you can ask during it, but in this replay, no chance to ask questions. You're gonna have to hit me up some other way. So what is SPIFFE? SPIFFE is a set of specifications. There are like 6 specifications that are all out on the SPIFFE website. I think it brings you to GitHub where they're actually hosted. You have the SPIFFE ID. You have 2 around SPIFFE verifiable identity documents, SVIDs. You have a couple around the workloads, and these are the endpoint and the API, and we'll see that in a bit. And then you have trust bundle and trust domain. What is a SPIFFE ID? You'll see this throughout the presentation. A SPIFFE ID is just a unique opaque string. It does not matter what the string is, in effect. It is simply a URI. Oftentimes that URI will come in the form of SPIFFE : the trust domain, which the SPIFFE identity represents, and then some workload identifier. And that's what it will look like. So when we see SPIFFE ID, that's what you can think of. SVIDs are about getting a secure, verifiable identity document, or SPIFFE, or SPIRE, SPIFFE, secure. It's one of those three. But what this is it's a cryptographically verifiable document. So it's that strong identity that we were talking about when it comes to workload identity. And SPIRE makes delivering or bootstrapping these SVIDs incredibly easy. We're going to see that happen here just in a moment. If we take a look at the overall architecture of SPIRE, it's going to look like this. You're going to see a SPIRE server, which SPIRE agents communicate to, and then workloads communicate to the SPIRE agent itself. We take a look at the SPIRE server, talks to the SPIRE agents, like we said, with the one purpose, which is to do this thing called node attestation. Node attestation is the way in which the SPIRE server is able to verify the agent that comes online is who the agent says it is and how the agent verifies the server. This is a little process, goes back to the term bootstrapping trust. This is really key because when your agent comes online, the SPIRE server needs to know who that agent is. It needs to know what identities the SPIRE server or SPIRE agent is allowed to deliver, and it needs to be able to trust that the SPIRE agent is who it says it is. So we're going to do that through a process called node attestation. Once that's done and attested to, the next step is to workload attestation. And so our workloads need to attest as well as to who they are with the SPIRE agent. And the SPIRE agent is actually going to introspect the workload itself. And the workload does not actually provide information to the SPIRE agent. It's all environmental. So if you're running in Amazon or if you're running locally, like I'll be doing here in a second, you can see that the SPIRE agent is doing this attestation of the workloads intrinsically based on the operating system itself. When you configure a SPIRE server, there are a few things that are important. You need the address and the port that the SPIRE server is going to listen on. It's going to listen on the underlay or the IP-based network. Underlay, important term, make note of that one. And you're going to have a trust domain that represents the identities which this SPIRE server is authoritative over, and TTL is time to live for how long you want documents to be good for. You're going to have a couple of plugins, some of which don't matter, the data store and the key manager. I mean, they matter, but in our example, we're going to be using local files for those. But the key one is that node attester plugin. The server must have a node attester, and the agent will use a node attester. Notice here in the configuration section of a SPIRE agent, we'll have a trust domain, and then we'll have the address and port, which the SPIRE agent will communicate to, and we're going to do an insecure bootstrapping in this case. I don't have time to get into how to configure SPIRE in a more robust way. Insecure bootstrap just means when the agent comes online, when you tell it to talk to the address and port that you tell it to talk to, it will just implicitly trust that it is a valid and safe and secure SPIRE server. Then I have some plugins that matter, the key manager and the node attester. The key manager is not particularly important right now. It is going to be the local file system. But the node attester and the workload attester, those will be important. And we'll see what those look like when we start looking at the actual configuration of SPIRE. First, we're going to talk about OpenZiti. OpenZiti is a zero trust overlay network. So its job in life is to shuttle bytes from one place to another safely and securely. And it does that using this term called an overlay network. Remember before we mentioned underlay, here is an overlay. So what is an overlay network? Generally speaking, it's easiest to deploy your overlay on the internet. So we're going to just call the entire internet our overlay network. And we're going to build our overlay network on top of the internet. You don't have to build it on the internet. You can build it entirely locally. Like I'm going to show you in a moment. You can have a private network. It just needs every device that's going to participate on your overlay network just needs to be addressable by every other piece of equipment, in effect. That's a simplified version. So it's easiest to just deploy your overlay network out on the internet. And your network is going to consist of a controller. And that controller's job is to authorize and authenticate clients. And then you'll have the overlay network itself, which will be consisting of routers, and routers all talk to another, making a full mesh, as well as talking to the controller. And all of this happens through mutual TLS. Every single piece of an overlay network has mutual TLS associated to it. That's all done in order to deliver secure connections to edge clients, whether it be your client API running on a local computer or an API running in Kubernetes on a service somewhere or at a Lambda, wherever it might be. The job in life is for the bytes to get safely and securely from one side to the other side, or vice versa. An important, really important key part of an OpenZiti overlay network is that you have no listening ports in your application itself. If you have an application embedded zero trust, like is shown here, you'll have no open ports. And you'll have no holes in your firewall. On neither side is there a hole in the firewall. Those are really key and vital pieces of information. Having no listening ports is such a huge superpower of an OpenZiti overlay network. It makes your application almost unattackable, almost. So here are some terms you'll hear when we talk about zero trust network access. What does that mean? Well, it means what you would expect it to mean. You have some zero trust appliance that is sitting at the edge of your local trusted network, your castle, if you will. And then you have secure transport between one router to another router or one device to another device, where you offload back to the underlay and you traverse the underlay network. And that would be zero trust network access. So on the left, we have private network space that you would traverse. We have your zero trust overlay. And then on the right, you have your private network space that you would traverse. Obviously, that's not the best. So this is like the first level of zero trust, but it's also the level of zero trust that you'll find most often. Most people consider this acceptable. I personally don't, but if that's good for you, then cool. You can do that with OpenZiti. You can do that with a lot of zero trust overlays. The next level is zero trust host access, where you basically have a little agent that runs on your local computer or on your server. And its job in life is to intercept packets at your client, shuttle them safely and securely across a total overlay all the way to the other side, where it offloads back to the underlay network. So underlay on the left, underlay on the right still, but that underlay network is now exclusively your local operating system. So on the right-hand side, you can offload to localhost, whatever port you're going toward. And that's great because now you're no longer traversing a local network. You're only traversing the host network. That's pretty cool. And finally, you have application access. If you can embed zero trust directly into your application on the client and the server side, you no longer have to even trust the host network because your application will have end-to-end encryption installed in it just by using an OpenZiti SDK. Finally, one layer after that, if you have a hardware rooted trust, a TPM or YubiKey or something along those lines, a CAC, then you can have hardware root of trust. And when you have a hardware root of trust, you have even lower amount of support or trust in the operating system. Still not nothing, which is representative by a little sliver there on the host and device. But you have a whole lot less trust that's necessary. And that would be like the penultimate at this point in time, I think, level of zero trust that you can get. Again, zero trust network, host, and application access. We're going to focus on host access and application access, and I'll actually demonstrate those two here in a moment. And so let's start looking at actual code, shall we? So let's actually start getting into it. When we look at the code itself, you'll see that it all comes from this particular GitHub repo. You can go out and get that right now. Take a picture, copy the URL, whatever it is, clone the repo. It only works in Linux. So if you are running Mac or Windows, I would urge you to fire up a virtual machine. If you're running Windows, then you can maybe use WSL. But if you're running in Mac, you're going to need a Linux machine. And if you're running Linux, then I would suggest a virtual machine too, just to avoid any port conflicts. But if you want to deal with those port conflicts, then that's fine. There are some ports that are, I mean, I don't think there are any that are normal. You know, these are all weird ports that I chose, but who knows, you might have a port conflict. So let's look at the baseline. The real baseline here, we're going to have no security whatsoever. So on the left, we'll have our server, and on the right, we'll have our client, and our client will communicate to our server. I'm doing everything on my local computer, And I'm doing that just to avoid the network because when I'm at the conference, you never know how conference network is. Here's what the server looks like. You can see we're going to call common create listener and common underlay create underlay listener, all with the purpose to serve non-TLS. So we're going to create a server, we're going to create an underlay listener to serve our service or our API without TLS. This is just our baseline. We'll have some imports. I won't show the imports. All this code is written in Go as well. Go is a great language for microservices and for API communication in general. We have some constants that are specified. We have the insecure port of 18080, the SPIRE-secured port 18081, and then the OpenZiti port, which technically won't matter and won't be used, but it's listed here because it's used for finding your service, and we'll see that in a minute. A couple more constants. We got our SPIFFE IDs at the bottom. We have the path to where the agent will create a domain socket, and that's how our workloads will attach to the agent. And we'll see all this in action. Here's our server code. Again, very basic. We're just going to make a new HTTP server using the Golang standard library, make a new serve mux for the purpose of adding handlers to that serve mux, and then associate the mux to the server and return the server. And so we'll have a couple of functions, index and math handler, that have to be looked at. And first, we're going to start with creating an underlay listener. So creating an underlay listener, very basic. It just calls, again, Golang standard library, net listen on TCP, and then listen on a particular port. Here are the two functions that service our API, obviously very basic. One just returns the word success, and one will take two inputs, input 1 and input 2, and an operator, and then just print out the result. Here's what our client's going to look like. It's going to create a math URL and add query parameters to it. It's just easier to make a phony API that does it this way so that it shows up on the slide nicely. And then finally, if you add a fourth parameter called show curl, it will actually show you how to make the exact same request using curl so that we can show that it's not just smoke and mirrors. We can actually use curl to hit our API. And then we'll just call the API. Calling the API, well, here's the create math and add parameters. Obviously, very simple stuff. Just setting these query params. Calling the API just makes a new HTTP request and then uses the HTTP default client to do the request, reads all the response and prints it out. All right, so let's go ahead and see this in action, shall we? If we flip over to this page right here, you'll see I've already run on this top pane up here. I've already run the demo, and when you're complete with the demo, it'll tell you at this point you should be able to run any of these client and servers in combination. And so they're separated into NoSecurity, SPIRE server, OpenZiti server, and SPIRE and OpenZiti. And we're going to run them in a row here. And so down here, if I run my NoSecurity server, you'll see that it says it's listening on 18080. I can then copy the demo invocation. And you see this is the equivalent curl. I got a result here. So it showed me my curl. I can execute the curl as well. But you can see I passed 10 times 2. Fun fact, if you don't Linux and Bash, if you don't quote the star, you'll glob, and that's not what you want. So make sure you quote the star. And we get our result. 10 times 2 is 20. If I can do that again, but instead of 10 times 2, I can do obviously 10 times 4 and get 40, and I'll get my equivalent curl that comes back. So let's go ahead and run the echo. By the way, the echo here is because if I don't run an echo, I won't get a new line. So let's go ahead and see this work first. And you'll see I get the exact same response. Result equals 40. If I change my parameter from 4 to 5, you'll see I get 50. So no smoke and mirrors. There's our insecure API doing its thing. All right, nothing fancy yet. We still haven't secured our API. So now we're going to talk about SPIRE. All right, so we've demonstrated we have an open port on the underlay 18080 without TLS. And what do we want to do? Well, we want to have a listening port on 18081, and we want it to be mutual TLS, meaning the SPIRE client or the SPIFFE client will have to supply a certificate to the server. The server will have to verify the certificate, and the server will also respond with the certificate back to the client. So in order to do that, we got to go through and configure our SPIRE server and our SPIRE agent. So here's a real basic view of the configuration block that you'll find from the sample code, the important bits. It binds on address 0.0.0 and port 8600. That's where the SPIRE server will start up and listen on the underlay. We'll establish our trust domain of OpenZiti because I work on OpenZiti, so everything has OpenZiti in it. And then JWT issuer, we'll see this used by OpenZiti later, not relevant for SPIRE just yet. Our plugins, we're going to use SQL and disk. These top two don't matter too much, but the one that does matter, the join token node attester plugin. This is how the SPIRE server is going to expect our agents to attest that the node is valid. And they do that through this GitHub page here. You can go out and read the documentation. Pretty good. There are many server node attester plugins. So if you notice, the word server is in front of node attester. So if you just go out there and get confused, make sure you look for server first, because there are agent node attesters too, and we'll see that in just a second. We're going to use the join token because the join token just makes this whole process easier. And for a quick demo like we're seeing today, it's the easiest. Then we're going to next we're going to configure our agent. So let's go ahead and get the agent configured. The 4 bits of that are important: the trust domain again, where the agent will find the SPIRE server, and then insecure bootstrap. This just says when the agent comes online and connects to localhost 8600 for the first time, it's going to trust that SPIRE server. For our demonstration purposes, this is perfectly valid, and probably perfectly valid for lots of people, even in production. But SPIRE doesn't recommend you do this. Instead, they would rather you configure it in a secure way. I don't have enough time to show you how to do that. We're going to use the disk manager plugin for the agent, but the 2 other plugins that are really important, that node attester, join token, and workload attester, Unix. Also pay attention, discover workload path is set to true. That will pop up here in a second. As promised, there are many node attesters, and there are agent node attesters as well. We're using the join token node attester, but there's Kubernetes and X509 and Azure, all kinds of good node attesters, all kinds of cool stuff to go out there and read about with SPIRE. We're going to use the SPIRE server to token generate, which generates a token for a particular SPIFFE ID. Again, this is the identity that the agent will be known as. This will be the parent in other invocations in the future. So we need to create and register it with the SPIFFE server. So we do that with token generate. That ends up giving us a token that looks like this. And then once we have that token, we're then going to run our agent. And we're going to pass that agent token in as the proof that the node is what it says it is. And that node attestation will then happen. And when that's complete, we'll now have a SPIRE server listening on 8600 and a SPIRE agent connecting on localhost 8600. And we'll have a couple of trust domains identified. There we go. So now we're going to authorize our workloads because, remember, we're trying to get that SPIRE agent to have the lock icon, mutual TLS, over to port 18081. In order to do that, we're going to need the SPIRE utility from the Go SPIFFE library to give us these SVIDs, the client SVID and the server SVID. So the client will send a secure SPIFFE verifiable identity document to the server, and the server will return one back to the client, and they'll both verify the certificate or the identity. And if it doesn't check out, if there is no identity presented, or if it's timed out or whatever, that will of course mean no connection. In order to do this, we're going to create an entry in SPIRE, the server itself. We're going to give the SPIFFE ID of JWT server, and we'll do this also for the client, but I'm just going to show you one invocation. So we're make a new identity called JWT server, and it's going to be a parent of OpenZiti/IDs, the agent itself. We're going to add some DNS options just so that our certificate has DNS sans in it. And then we're going to use the Unix path selector for our workload attestation. And we'll see that work in a second. I think this is really neat. There are many workload attesters. We are using Unix in our use case here, but there are Kubernetes ones and Docker ones. The Kubernetes one's very extensive. The Unix one itself, has a few different parameters that you can use. You can use a user ID, group ID, the group number, etc., those sort of things. We're using the path selector, and we're using it with discover workload path equals true, not false, because we're going to use that workload path. But you could also use the SHA-256 of your executable. If you wanted to layer in additional selectors and make it a bit more secure, you can do that sort of thing as well if you'd like. All right, so at this point, we should have our SPIRE server, and our SPIRE client has not been configured yet. We have no client code, but we have a listening port on 18081, or at least we have the underpinnings to make this happen. So now let's look at the SPIRE code itself, and that should just say code, not client code. Here's what the server looks like. As you recall, this is the first server that we had, so clearly our SPIRE server, it must be really complicated. Let's look at it. Oh wow, it's not so complicated at all. It's only like 9 lines of total code with some hand waving around the fact that we have our common functions that we're going to invoke, like configure mutual TLS, but we'll see those in a minute. It's really not that much code. Taking a look, we can see we create a server using the Golang standard library. We're going to end up making that create common server. We already saw that once before. This is exactly what we've already shown. Then we're going to use the Go SPIFFE library in order to create a client options. And that client options, its whole job is just to tell the runtime, where is the agent? How am I going to find it? And it's going to use that Unix domain socket that you saw in the constants earlier. Then we'll call configure from mutual TLS, pass in Goism. This is a context.background. We don't need to get into that. Pass in our server that we made from up here and pass in our options. Once we're done with that, then we're going to serve TLS in this case, which is cool. We're going to serve that on the underlay. So we'll make an underlay listener and then we'll serve our TLS. Configure for mutual TLS, like I said, very few lines of code. It calls new X509 source from the Go SPIFFE library. And what that will do is it will make a new source that allows us to have continually rotating certificates to retrieve the certificates, to bootstrap everything it needs to bootstrap. That'll all be taken care of by that one source. And then by this TLS config MTLS server config. That is really the key of what happens here. We're making a TLS config that is then used in our server that we passed in up here. See, server TLS config. So this configures our server with server-side mutual TLS, and it's going to expect SPIFFE client ID. So again, we're passing in this client ID, and we're authorizing only that SPIFFE ID. So if that SPIFFE ID shows up, great, our server will answer. And if it doesn't, then too bad, our server will not answer. Remember, that's so that we can serve TLS. And fun fact about the Golang standard library, if you configure a TLS config in your listener like we did, then the key and the cert are just left blank. I find that goofy, but that's the standard library. So that's what those two blanks are. So now we're serving TLS, and we're not serving HTTP. We're serving TLS. So now we have the whole thing. We've got mutual TLS client and server, and we have our SPIRE server and our SPIRE agent set up, and we have a secure API. We look at what the code looks like of the client. It doesn't look too much different. We still call create math URL, but instead of the insecure port, we pass whatever port we want, our SPIRE secure port, and HTTPS, not HTTP. We then make that options, and remember we have a server and a client. So this client code also needs to make an options that tells the client where to find the agent so that the workload can be attested to. And then we call secure default HTTP client with SPIRE MTLS, which is a function I wrote. It looks like this, not very big. I probably could have put that on the prior page. It just makes a SPIRE MTLS. I probably should have shown that code. It's in the GitHub repo. You can go look at it. And then adds that transport to the default client. And that is all it does. So like 6 lines of code, something like that. So let's go ahead and look at this in action too. Since I've already run that bootstrap script, I can just start the SPIRE server. It'll listen on 18081. and I can run the SPIRE client. And just like before, we get a result. Whoop-de-doo, big deal. Why is that cool? It's cool because we had to specify a certificate and a key in order to connect to that server. Remember, we've just delivered mutual TLS with 10, 20, 50 lines of code, whatever it might be, and in no time, so fast. And so if we go ahead and run our curl statement, you'll see we get our result. Well, like I said, big deal. That's what we expect to see. But what happens if I get rid of the key and the certificate and issue that response? You'll see I get no response from curl, nothing. And up here in the server, you can see the server rejecting that client. That client did not provide a certificate. I'm sorry, it is no good. Fantastic. So already we now have configured our entire world in the same way that we said we would, and we've blown everybody's minds, I hope. And let's take a look at what we've done. So just in 5 to 50 lines of code, we have deployed our SPIRE server and our SPIRE agent, modified a little bit of source code. We've gotten mutual TLS added to our entire solution. We have mutually secured both the client and the server. That's what MTLS means. We've got end-to-end encryption. If your application is terminating your HTTPS endpoint, then I would consider that end-to-end encryption. We do have to be careful though, because HTTP has lots of ways for a person in the middle to get in there and for us to lose that end-to-end encryptionness. So we do have to be careful with that. But we do have implicit attestation and certificate key delivery, meaning I didn't have to deliver a certificate or a key to my client. The SPIRE agent and SPIRE server worked together to do that. And my certificates are now short-lived and automatically rolling. All of this happened with just a few lines of code and with very little work on my side. And now we have a pretty darn secure API. All right, let's go ahead and look at how we would do that sort of thing using OpenZiti. As a reminder, we've got our insecure server that we want to turn secure. So we're going to make an OpenZiti server and an OpenZiti client. And we're not going to use the SPIRE server and agent just yet. So we're going to take those out of the picture. But what we are going to have is we're going to have no open ports, and we'll have end-to-end encryption. The OpenZiti overlay works by the server and the client, both establishing connections to the router on port 3022. And those are underlay mutual TLS connections, so lock icon, lock icon. And they'll connect to the controller in order to do authentication, authorization type stuff on port 1280. And then we'll have a solution that has no open ports, and we'll see that. Usually, when we bootstrap trust, this is the flow that we go through. We deliver a JWT, a JOT, and enroll, and that's still available to us, but we're going to actually use the SPIRE and SPIRE agent and server in this case to do that delivery. So we are going to use that SPIRE agent and server since we have it locally. Let's talk about how we configure our OpenZiti overlay, because in order to enable the OpenZiti server and client, we do have to configure the overlay. First thing we need is we need to make an external JWT signer, which is a OpenZiti object that just informs OpenZiti where it can go in order to verify an incoming JWT is valid. And we're going to use a JWT or a JOT for authenticating our client and our server to the OpenZiti overlay. So we provide a external JWT signer, we name it, and we give it a JWKS endpoint, which SPIRE provides. And then we give it an audience, and this audience is important. Our JWT must show up with this particular audience. And then we'll make a authentication policy, an auth policy, and we'll do that where we'll allow the primary authentication to be the external JWT, and then we'll also give the external JWT signer as the signer, which is valid for the particular auth policy. And so that will configure OpenZiti to use the SPIRE provided JWT and the SPIRE provided JWKS endpoint as an authentication tier. Then we'll make two identities and we'll associate those identities with the authentication policy. So you can see the auth policy is used here. We'll make a a service that is the client and a service that is the server. Both of our applications need a client and a server. We'll give them an associated external ID. This is a claim specified as the subject in the JWT. This is how OpenZiti will identify the incoming connection. So we'll get a JWT from the SPIRE agent. The workload itself will either be JWT client or JWT server, and then we will use those to find the associated strong identity in Ziti's world. And then we'll give a couple attributes. The server will be the server and the client will be the client. And then we'll create configuration and service in OpenZiti. So in this case, we have a config, and that config is useful because it will be how the code finds the service, the OpenZiti service, in which to dial. So the client will use what looks like an underlay address of OpenZiti.ziti and on port 18082. And that will be how the client locates the correct OpenZiti service in order to send the data from the client to the server. Then we'll go through and we'll do the same thing and we'll configure another service. In this case, this is going to be our OpenZiti and SPIRE enabled service. And we'll see this in action later. The only important point here is that it is OpenZiti.spire.ziti. The intercept address is different. Then we'll make a couple of service policies. Zero trust, the least privilege motto, means only identities that are authorized to access the things that they're authorized to can. And so we'll say any service that has demo services as its attribute, role attribute, will be able to be secured by will be able to be bound by any identity that has the role of server, demo services server, and any client can dial the same service. So demo services clients can dial the demo services. Demo services server can bind the demo services. So this basically means the servers can host the service and the clients can dial the service. Simple as that. Let's go ahead and look at the code. Again, this is what the original server with no security looks like. And this is what it looks like with extra security, with OpenZiti securing that service. We create our server, we make our workload options, but this time we're going to fetch a JWT. So before, we were not fetching a JWT, we were using the options to create a SPIRE connection, mutual TLS connection. This time, we're going to use SPIRE to return to us a JWT. And with that JWT, we're then going to make an OpenZiti overlay listener. This is not an underlay listener, this is an overlay listener. There will be no port available once we create that server. So then we'll use that to serve. What do you mean serve? Wait a minute. No TLS. This is going to have end-to-end encryption without TLS. So you can encrypt a payload stream without having TLS. I know that it sounds a little weird, but that's what's going to happen. OpenZiti has libraries built into it, which will allow you to encrypt your stream without having the classic TLS type of encryption. So when you look at the stream on the wire, it of course will have mutual TLS. That's already happening under the hood anyway. Your application stream is going to be HTTP. Hopefully that's obvious. Hopefully that makes sense. And if not, then we can always talk about that. The client code is going to look relatively the same. We're going to make that math URL. We're still going to use HTTP, but instead of localhost, we're going to use OpenZiti.ziti as our URL that we're going to find. And then since we are making a client, we're going to use that JWT. We're going to fetch, in this case, the client side JWT. Then we'll secure our default client with that JWT. And that's what we'll end up doing. Again, notice HTTP and secure the default client. Creating a Zitified transport is relatively straightforward. This is going to be used in order to secure the default client. If we go back a level, we see we're creating a Zitified transport here. This is how we actually do it. This is how many lines of code it takes to actually create an HTTP transport that you can use to secure your client. We're going to go ahead and do that. We'll use the JWT provided from SPIRE to make a new credentials object. And then we'll use that credentials object along with the the location of the controller in order to authenticate our OpenZiti context. And then by the time we're done, we will just return that transport along with a new dialer function inside the transport. Again, I was saying before how the Golang standard abstractions are amazing for this type of stuff. But there are other languages, Java. We also have a Java-based SDK. You can, you don't have to use Golang. You can use a bunch of different languages. But this is the basic flow. You get a transport or you secure your client using the OpenZiti overlay, and then you basically send your bytes. And so when we're done, we're going to have no open ports, and we're going to have OpenZiti client that has end-to-end encryption, and we'll be able to see that in action too. All right, so let's see that in action. I missed my little demo slide. So let's go ahead and see that. So here's our OpenZiti server. You'll see when I start this up, it'll tell you that there's no overlay port, right? We have no underlay port. So I can run ss -lntp and pipe for grep to 180. Just look for anything 180 in the case 82, but it doesn't matter. There are no ports that have 180 open. So let's go ahead and run the curl statement. Sorry, not the curl statement, the client statement. When we do that, you'll see, hey, we get the same result. There's our 20. And we're able to run a curl that does the same thing. So let's go ahead and run the curl. Oh, wait a minute. Our curl didn't work. Why is that? Our curl is connecting to 18082. Well, it makes sense that it doesn't work, right? There are no ports available to curl. So when I'm running curl, this would be the zero trust host access way. I need something that can intercept this address and allow it to work. So what I'm going to do is I'm going to install a identity into, actually, I've got to move the identity first, I think. Let's move the one that created local Docker user, and I'll move that to my temp directory. And now when I go back over to here, I can add an identity, and I can do local Docker user. And when I do that, I'll have a new user, which has 2 new services available to it. And so now if I come back and I do this same exact curl that I did before, which did not succeed, now it succeeds and I get a result of 20. So what I've done is I've actually enabled zero trust host access through the use of this ZT Desktop Edge for Windows. If I stop my locally running tunneler, try to access it again, you'll see I can't. And obviously if I start it back up again, when I start this back up and it succeeds in starting, then we'll be able to access that URL again. And so that's zero trust host access at work. So that's a little extra that you get from the OpenZiti overlay. So we still have end-to-end encryption. Actually, let's go back to the presentation. So we still have end-to-end encryption. We've still got these 5, 6, 10, 50 lines of code, small amounts of code, but we also have our implicit attestation and secret delivery. Since I used SPIRE and the SPIRE agent to deliver that secret, I didn't have to configure my OpenZiti client or my OpenZiti server. I still have short-lived automatic rotation. I still have end-to-end encryption, but this time I get end-to-end encryption that's guaranteed by OpenZiti, which means even though while it traverses the network, it's going to be mutually TLS secured because that's how every OpenZiti overlay network is created, you'll also have end-to-end encryption involved with an OpenZiti overlay. You get that for, and it'll guarantee that your traffic will land all the way at its expected identity, regardless of attempts to person in the middle it. We also have no listening ports now, which is, I think, the best and the strongest feature of OpenZiti. You'll have no listening ports. It makes you almost impervious to side channel attacks. If another pod or another local process tries to snoop the network, it's going to find nothing. Like that is amazing. You'll have ubiquitous connectivity. As I mentioned, you can deploy your OpenZiti overlay on the internet. And if you do that, regardless of where you are, your clients will be able to connect into the internet, across the internet. As long as they have outbound internet, they'll be able to connect to the edge routers and to the controller, all through mutual TLS. And you'll be able to reach down even into other locations that you weren't able to before. So you don't have to open firewall holes. That's huge, right? So with the SPIRE-based approach, which is already pretty good mutual TLS, you'll be able to have the same sort of idea, end-to-end encryption, but not have to open any holes in your firewalls. And then you'll authorize before connecting. So remember before, when we were running our server, our SPIRE server, when the client, when I used curl and I didn't supply a certificate, I was told by the server that an insecure attempt had been happened, and then the connection was cut. So I actually connected to that server before being authorized. So an actual connection was established before my code kicked in, and my code then, the SPIRE code, terminated the connection. Well, 0 days do happen. So if you have a 0 day out there, it's really nice to not be able to even connect to that server before rejecting the traffic. And with OpenZiti, you get that baked into. So let's take this up one notch and let's add SPIRE and OpenZiti together. So now we're actually going to create a mutual TLS demo where we have a OpenZiti server that presents a certificate, which an OpenZiti client communicates to the OpenZiti server over that certificate as well, and over OpenZiti. So you get the benefits of OpenZiti plus the benefits of SPIRE mutual TLS. And I think that'll be a pretty interesting and compelling demo. Let's go ahead and start up the server that is configured for SPIRE and OpenZiti. Again, no open port, even though I'm starting a server up. We'll do that SS again. No open ports still. Just to prove that my SS does work, if I look for 3022, that is the router, or 1280, that is my controller, you will see there are actually listening ports on this machine. And then if I do 8600, come on, 8600. Actually, let me put in a sudo in this one, and that way you'll see the process name. You'll see that that's the SPIRE server. So there are listening ports. Now let's run the client. Thank you for copying when I didn't want you to copy. And now when I run the client, you'll see I get my response of 20. And then, of course, you know it doesn't work unless you're running OpenZiti. And you still have to supply a key and a cert and a key. So if I run my client now, you'll see I get my result because my Ziti Desktop Edge for Windows is running. But if I take off the cert and the key, as you would expect, I get no response. If I put that back in, I get my response. And if I turn off my tunneler, as you would expect, I get no response. And so, I mean, I think that's a pretty whiz-bang demo. It's easy to gloss over just how cool that is. But we now have all the same stuff we had before. We have mutual TLS. We have no listening ports. We're authorizing before connecting now as well. We've got no firewalls or ACLs that had to be updated. And we have mutual TLS. I mean, that's just amazing to me. So I hope that that's as amazing you think it's as amazing as I think it is. And so if you do, and you want to get OpenZiti or SPIRE, you want to go out to SPIFFE.io. It's not SPIRE.io, it's SPIFFE.io. And you want to go to github.com/SPIFFE or SPIRE. That's where you can get SPIRE at, or OpenZiti.io. Same GitHub URL at github.com, OpenZiti/Ziti. And if you think that these projects are as cool as I do, go out and give them a GitHub star, because it really does help spread the word about SPIRE and how neat it is, spread the word about OpenZiti, about how neat it is, show people how easy it was to secure your API. And that's all I have. I got some socials I can pop up. So if you wanted to go and hit me up on Twitter or OpenZiti on Twitter, or you want to contact me, I work for NetFoundry. Yeah, and that is everything. So thank you very much, and I hope you enjoyed the presentation. Oh, and don't forget, you can go back to GitHub and get all of the code. Let me go back and find the code for you so that you can, nope, let me go back and find the code in case you want that URL. Where is all the code? Right here. There you go. Thank you very much.